Characteristics of an element. Now, in this lesson, we're going to be able to figure out the traits of an element, its group number, period number, orbital block that it belongs in, without even needing a periodic table. Before we do that, though, let's establish some ground rules for inferring these traits. The first one is that the last numeral of a group number is, or here I'll put equals, all right, it equals the number of electrons, the number of valence electrons. And this VE stands for valence electrons. So let's say, for example, we have group 15. The last number would be 5, so this has 5 valence electrons. All right, that's the first rule. Now we got the second rule. The second rule is the N, also known, you should know this by now, the principal quantum number. The N value of the highest occupied energy level is the period number. And you should already know this by now. Example, if N is equal to 6, then the period number equals 6. Simple as that. Now let's go to our third rule. Here's where it gets a little bit more complex. And this is going to be tied into a formula structure as well as a sentence. The square of the N value is equal to the total number of orbitals in that energy level. Let's look at an example, because this is going to be paired up with a premise here where, since each orbital can have a max of 2 electrons, the max number then in any principal energy level is 2n squared. Let's look at that example I mentioned. If n is equal to 2, let's use this n squared formula. The n squared formula is written up here on this first premise. The square of the n value is equal to the total number of orbitals. So if 2 is substituted, this would give you 4. So this would mean that there are 4 orbitals. 4 orbitals. Is there a proof? Let's figure it out if it's actually true. If there are 4 orbitals and n is equal to 2, remember, if n is equal to 2, that means the period is 2, because they are the same. So if it's the second period, what subshells exist for the second period? Well, remember the off pause. 1s, 2s, 2p, remember that? 3s, 3p, 3d, etc. The 2s and the 2p's are the ones that exist. How many orbitals are there? 1, 2, 3, 4. Therefore, this is correct. There are 4 orbitals. Works out pretty well. Now let's look at the total number of electrons. What would that be? The total number of electrons. Well, you know that each one can have a maximum of 2 electrons, as written here. Pauli exclusion principle. So if you were to add up all of these together, you end up getting 8. So you get 8 electrons. Now, is that true? Do we have proof for that? This can also be identified as 2n squared. Well, let's substitute it. 2 squared, 4 times 2 gives you 8. So it seems to make sense pretty good. Now I also want you all to remember here, I'm going to put a star. This is quite important. If there are 8 electrons, this means that there are 8 elements in that period. And if you were to look on a periodic table, let's say it kind of looks like that, something like that, and you were to count from the second period, so let's say if this is the first period, this is the second period, if you were to count these elements, 1, 2, 3, 4, 5, 6, 7, 8, you should be able to see 8. Alright, if n is equal to 3, what do we end up getting? So if n is equal to 3, we know that if we square it, it's going to give us 9. So are there 9 orbitals? What's the proof for that? Well, we've already written up here that the 3s's, the 3p's, and the 3d's exist for that principal quantum number, the principal quantum number of 3. There is no 3f's. So if we were to draw it out, 3s, 3p, and 3d, and you count down the number of orbitals, 1, 2, 3, 4, 5, 6, 7, 8, 9. Turns out to be correct. So that's it for the number of orbitals, and we've proved it. Now, we can do something similar, but how about the total number of electrons? How do we do this? The total number of electrons. This can be a little bit complicated because we need to distinguish between the total number of electrons versus the total number of valence electrons that an element can have. Anyways, in order for me to clarify on that point that I just made, I want us to continue building up these energy levels, these subshells of increasing energy. So if we were to continue to draw this, and I want to show you how this all relates back to this 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. And we have 6s, 6p, 6d, 7s, 7p. Alright. And of course, they go in this order here. And if we were to look at our 3s's, 3p's, and 3d's, they're right here. We have our 3s's, then our next one will be the 3p's, but then after that it's the 4s before we see that 3d. That's okay, we got to add that 4s first. So I'm going to add that 4s over here. Okay, so that's going to be 1 as well. So after the 4s, it gets to our 3d. And then we'll be able to find the total number of electrons. Now, if I do this, what do you think of it? Do you think it's incorrect or if it's correct? So if I were to write the total number of electrons, so there's 2 here. Okay, I'll do it in a different color. So let's say there's 2 here. And then I add up all of these ones. 1, 2, 3, 4, 5, 6. And then after that I go to my 4s. And then I go to my 3ds. And then I add these ones. If you were to count all of these up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It seems as if we've gotten 20 electrons in total. So should that be the answer? Should it be 20? No. The number is still 18. Again, how do we prove this? Well, we know 2n squared is what we should be using to determine the total number of electrons, right? The max number of electrons in the principal energy level. So if we have 2, and then 3 is our n value, 3, 3, 9 times 2 gives you 18. Hence why we got 18. But we figured out that the 4s value kind of becomes a barrier. But why do we ignore it? We ignore it because it's not a 3 principal quantum number. Even though it needs to be filled up first, before we start stacking all of these electrons, it doesn't matter. We have to understand that that happens, but when you count the total number of electrons, make sure that you first do this, but then you're just going to count the total number of electrons on that 3. The 3 S's, the 3 P's, and 3 D's. Don't worry about the 4 S's. Just know that it needs to be filled up first. Let's do another example. This next example here, I'm going to have n is equal to 4. And same thing. I would like you to tell me what is the number of orbitals. As well, tell me, can you prove it? And then after that, the total number of electrons. And then after that, does it follow our golden rule formula, 2n squared? I want you to pause the video and give it a try right now, please. Alright, hopefully you've tried it out. Let's do it together. We have n squared, because we're using this premise here to find out the total number of orbitals. This should give us 16. Do we have proof for that? Let's write out our principal quantum numbers of 4s. So we care about, as you can see, the 4 S's, the 4 P's, the 4 D's, and the 4 F's. These are the ones that we're trying to reach. As long as we can reach all of these, we are good. But along the way, there may be some challenges, and then I'll show you how that looks like. Let's have our 4 S's. And then after the 4 S's, what is after? We get the 3 D's. So the 4 P's would be here, so the 3 D's may be here. After the 3 D's, we end up getting our 4 P's. After the 4 P's, let's go to our 5S. After the 5S, let's go to the 4 D's. After the 4 D's, let's go to the 5 P's. After the 5 P's, the 6 S's. And after the 6 S, we finally get to our 4 F's that we're just trying to get to. And what we can do now is fill up these electrons. Now, let's do it accordingly. So we got our 4 S's, then our 3 D's. For learning purposes, I'm just going to do it correctly in order here. After the 3 D's, go to our 4 P's. Make sure to apply Hund's rule for every single step. 4 P, then we go to our 5 S's. After the 5 S's, you go to the 4 D's. After the 4 D's, we go to our 5 P's. Then after the 5 P's, we go to our 6 S. After the 6 S, you go to our 4 F's. 7, 14. Okay, now that we've done all of this, we need to find the total number of electrons. Total number of electrons. Now, what is the total number of electrons for the principal quantum number 4? If you were to look at it in terms of its valence, this would be it. All right? How do we know that? Well, these are the 4s. So if you were to count them all up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, we end up getting 32. So the total number of electrons is 32. And we can prove this with our formula 2n squared. if we end up putting 4 over here, you square it, 16 times 2 gives you 32. So it ends up working out quite well. I know that we have to fill up all of these first. We fill up the 3Ds, and then the 5S's, and then the 5P's, and then the 6S's intermittently throughout. But when we look at the total number of electrons, we only care about the 4s. Now I want to make a big distinction here. This is quite important. Of the total number of electrons in a shell versus the total amount of valence electrons that an element can have. It's very important that we exhibit the differences between the two before we move on to any questions. So let's have a look at those. Let's look at this premise here, where I'm going to state very explicitly that the shells do not equal the orbitals. And I think a lot of individuals get confused with these two terms. The shells are not the orbitals, because guess what? The orbitals, so since electrons in different shells are in the different orbitals. So electrons are in different shells. So the shells are a collective amount of electrons, whereas the orbitals are electrons in the different shells. The orbitals must be in different types of shells depending on the principal quantum number. So if n is equal to 1, this is our first shell. And if n is equal to 2, again, that is our second shell. If n is equal to 3, that is our third. If n is equal to 4, that is our fourth. So in our fourth shell, for example, there are various amounts of orbitals in these different shells. So the orbitals can exist not just in the n is equal to 4, but those same orbitals could exist in the n is equal to 3, or could also exist in the n is equal to 2. In case you're still confused, let me show you with a few examples. In order to continue this thought, since electrons in different shells will have different n, or the principal quantum. It's important to distinguish that. Let me show you with a few examples. Our first example, let's look at our first shell. In our first shell, this has one orbital. And we should know this by now based on this. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 7s, 7p. So our first shell has just one orbital because, as you can see, there is only one s. But in our second shell, a little bit different, right? We now have 4 orbitals. Why is this the case? Well, let's put in brackets here. What do we see for our second shell? We have our 2 s's and we have our 2 p's. So it's a 2p and a 2s. And remember, this has 1 orbital, but the p's can have up to 3. So if you add these all up, it gives you 4, like in the previous example we did. Let's look at our third shell. In our third shell, we now have 9 orbitals. And we've already done this together in the previous page. 9 orbitals because of our third one, we have our 3 s's, we also have our 3 p's, and we also have our 3 d's. This has 1, this has 3, this has 5. You count them all up, 5 plus 3 plus 1. All right? Let's do one more. Let's do our fourth shell. Our fourth shell has 16 orbitals. if we were to look at what we have the 4 S's, the 4 P's, the 4 D's, and the 4 F's. This has 1, this has 3, this has 5, and this one last up here has 7. 1, 2, 3, 4, 5, 6, 7. You were to add them all up, you end up getting 16. So that's how we end up showing you that there are different orbitals, the S's, the P's, the D's, the F's, within the different types of subshells. So they are not the same. So I'm going to just put in here in a star. This is also known as the orbitals. So the S, the P's, the D's, the F's that I just mentioned, of various kinds, become available as we go to a shell with higher n. And again, our n is our principal quantum number. Let's do an example together. If we look at something like 7s, we need to understand that this 7 here represents the shell, or the principal quantum number. This here represents our orbital. Now each orbital, remember, can have a max of 2 electrons. And they are spinned upwards or they're spinned downwards. So these electrons are important to discuss, because if we look at our s orbital, we're still focused on the orbitals right now, our s orbitals can have how many? It can have up to 2 electrons because it only has one orbital. Our p's can have up to 6 electrons. Because how many orbitals are there? Well, there are 3 orbitals. That's 3 times 2 gives you 6. Next we have our D's. And this can have up to 10 electrons. How do we know that? Because we have 5 orbitals. 5 times 2 gives you 10. So the electrons per shell, if you were to look at the number of electrons per shell, it adds up this way. Electrons per shell. So for the n is equal to 1 shell, what do we get? Well, we have 1 times 2 ends up giving us 2. If we do the same thing for n is equal to 2, so then you just end up getting 4. Then you multiply that by 2, and then you end up getting 8. Now, why is that the case? Why did I put 1 times 2 and 4 times 2? Because it's the number of orbitals. This orbital here, I'll do it in green. This is the orbital within that first shell. You multiply it by 2 because you can have a maximum of 2 electrons in each orbital. So if this is 1, and I got that from up here, and you were to multiply it by the maximum amount of 2 electrons, you end up getting 2 electrons for that shell. You do something similar for the 4th orbital. So 4 on the second shell can have a maximum of 4 orbitals. You multiply it by 2, gives you 8. So you get a maximum of 8. I'm going to continue it off on the side here. If I were to do n is equal to 3 shell, we look at our number of orbitals. We end up having 9. So you just do 9 times 2 gives you 18. And then we do n is equal to 4 shell. Right up here we're at 16. 16 times 2 gives you 32. That's how we got those values. The 2, 8, 18, and the 32. I'm just spreading it out here to let you know the differences between the shells and the orbitals. And they may have relation, but they are quite different. It's very important to distinguish that. Let's try another example. The electron total number in a shell, like I've said already, does not equal the number of valence electrons for an element. If I were to get an example here, and let's say we have n is equal to 3. We've established already if n is equal to 3, we're going to have 18 electrons. If there is a total of 18 electrons, this does not equal the amount of valence electrons for a particular element within that period, because there are only 8 valence electrons for that element. Now, how does this make sense? Because the 3D orbital must be filled first. The 3D orbitals pretty much aren't filled yet. The 3D orbital isn't filled. And if it's not filled, then it can't continue until the 4th period is done. Let's have a look at our periodic table. If we look over here, and this here is our 3, our third shell, if we're to count it up, 1, 2, 3. If that's the case, and this is our third one, let's count. This is 1 electron. Sorry, one electron. This is our second one. And if we're to continue on our third period, we would skip all the way to here. 3, 4, 5, 6, 7, 8. This is how I got this value of only 8 valence electrons. Why? Because the 3D orbital isn't filled yet. Our 3D orbital is actually here. Now, most periodic tables, or a lot of periodic tables, they have them separated, where this orbital block over here, the D block, is kind of separate, because a standard periodic table like this can be a little bit confusing, where a lot of the junior periodic tables maybe look like this, and it could be confusing when we learn this kind of concept. The 3D is not over here. The 3D is in the layer after it. And it actually comes after the 4s. As we can see here, the 3D comes after the 4s. So if there's an element that belongs here in our period, it must be known that this comes first, our 3s's over here, and then our 3p's over here. But right after that, it goes straight up to our 4s's. Right, this here is a 4s. And then eventually we can go here, which is our 3d's. So because it's not filled up yet, because the 4s's need to be filled first, there's only a total number of 8 valence electrons for an element in that shell. Let's try another example. Or actually, before we give an example, let me show you with another type of illustration in case this is still kind of confusing, because this is very important to comprehend. If we were to look at, let's say, a subshell method, so if we had here 3s, and then we had our 3p's, and then we go straight up to our 4s's, and then we go to our 3d's. 1, 2, 3, 4, 5. You have our 3d's. And if we were to fill them all up, right after the 3p's, we go to our 4s's, and then we go to our 3d's. And then we fill it. However, an easy way to think about this is, if you were looking at your 3's, and we want to see the total number of valence electrons, again, not total number of electrons in a shell, not that, talk about the number of valence electrons for the element, I want you to stop at where you encounter the next highest principal quantum number. You see how we are starting at the 3s, we're starting at the 3p, and then as we continue to go along, we cannot go to our 3ds, we need to stop at the 4s. 4s is the next highest principal quantum number. It's a different number. It's 4, it's not 3. So this is where we stop. So if we stop here, we can't even continue here. Hence we have 2, 4, 6, 8. Thereby on our periodic table, 1, 2, 3, 4, 5, 6, 7, 8. That's where it stops. Cannot continue to fill up that 3D. This is what it's meant here, because the 3 orbital isn't filled until the 4th period is filled. Hope this makes a lot more sense to you. But if we look at another way, and let's say I do the same thing, but instead of that, I now do the whole thing. So I don't stop there. I continue until I finish up getting my 3Ds, because I care now, again, this here was for the total number of valence electrons. Now this is for the total electrons in the shell. Let's fill it up. And I can keep going, okay? I can keep going with my 4s because I'm looking for the total number of electrons in that shell. I can go up higher. I'm not limited to that next principal quantum number. Now, what can we look at? We look at the total number of valence electrons. Sorry, total number of electrons. And if you were to count it up, 2, 4, 6, 8, 10, 12, 14, 16, 18. Now you end up getting that number of 18. Because this here represents the total number of electrons in that shell. Because other things are being filled up before it, that's fine. We don't care. Let them fill up. We need to follow the rule. Once we do that, we get to figure out at the end, once all of these orbitals are filled, we can count up the total amount of electrons in that shell. Up until then, if we want to find just the number of valence electrons for that element, stop at the principal. Let's try another example. We'll try n is equal to 4. Let's look at n is equal to 4. And let's look at the two differences between the total electron number and the total valence electron. If I were to write this out, we are starting at our 4s. After that, what do we have? After the 4s, we end up going up all the way to our 3d. So let's make a 3d over here. After the 3d, we go to our 4p's. After the 4p's, we go to the 5s. After the 5s, we go to the 4d's. Now, I can kind of stop there because I've already finished all up to my 4. Actually, no, sorry, there is a 4f, so we actually got to continue. But let's first do our total number of electrons. Sorry, our number of valence electrons first. And then over here, I'll do the total electron. So if this is our 4s and our 4p, everything's fine and dandy because we haven't encountered our highest principal quantum number just yet, up until here. Once I've written out that 5s, we have reached that new principal quantum number. That's going to be paused. We're halted over there. Let's show you. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. Just keep going. After the 4p's, we go to our 5 s's. We're done. We cannot continue. We cannot get to our 4Ds because our 5Ds come first. Sorry, our 5 s's here comes first. So we obviously can't get to the 4Ds because our 5 s's stopped us. Let's count the total number of electrons. We have not total number of electrons, total number of valence electrons. So we have here 2, 4, 6, 8, 10, 12, 14, 16, 18. We are now at 18 valence electrons because we couldn't surpass any higher than that. This is the valence electron number. But if we were to do something similar, and let's keep going until all of our 4Ds are completed, then we get a different value. Let's draw it again. Our 4 s's, our 3Ds over here, and then our 4 p's, and then our 5 s's. After the 5 s's, you get to your 4Ds. After the 4Ds, we need to go to our 5 p's. After the 5 p's, we go to the 6 s's. So we got to get all the way up to the 6 s's to be filled first before we can even start the 4 f's. Let's do it up. So we're going to fill up these. Then we fill up our 3Ds. Then we do our 4 p's. After the 4 p's, you go to your 5 s's. After the 5 s's, you go to your 4Ds. After the 4Ds, you go to your 5 p's. And after the 5 p's, you go to your 6 s's. After the 6 s's, you finally get to your 4 f's. 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, in order for the total electron number, we only care about the 4's because we're only looking at the n is equal to 4. So let's count it up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. This is how this all works out. We have to be able to distinguish between the total number of electrons and the total valence electrons for that element. And I'm sure you're quite familiar with a teaching back in the junior grades with 288. And these 288s, this rule you learned up to here for the calcium, anything more than that couldn't do. These were the valence electron numbers. The 288 doesn't mean the total electron number. It means the valence electron number. In fact, we can actually add the 18 there as well. We've already done it in the previous examples throughout this video, where for the valence electron number, so these here are the valence electrons. Our first shell has 2, second shell has 8. We just did the n is equal to 3. We found out that has 8. In case you kind of forgot, backplay this video a bit to see that. We got 8 valence electrons. And then down here is n is equal to 4. 18. These were the valence electron numbers. I know you don't really look at this in those grades. You just looked at the 288 rule. This was referring to the total valence electron number. However, and we just added this 18 now. It's a new addition. However, we also need to look at another phenomenon where we look at the total number of electrons. So the total number of electrons, we would have 2, and then we would have 8, and then we would have 18, and then we would have 32. And again, we just did the 32 one over here. And shortly before that, we did the total number of electrons for the n is equal to 3, we ended up getting 18. Because we looked at the total number of electrons after we filled these other substituents in order to get there, to get the total number of electrons for that principal quantum number. So here, well, why did I write that out? Not valence electron number, this is the total number of electrons in that shell. It's very important to distinguish the two. I'm going to be looking at one more example where it's quite short and we put all of this into perspective and we look at finding, inferring traits of an element, looking just at the, looking for the group number, the period number, and the orbital block. Let's have a look at an example here with AR and 4s2 and 3d8. This one I believe is iron. We need to figure out how to find the period number, the block, as well as the group. And there is a particular formula that you would need to know in order to do these kind of questions. There are different types of formulas that are out there. However, I want to share with you a formula that, a few formulas that I think are probably the best and tend to be the ones that stand up to scrutiny the best, but it's totally up to you. If I were to look at the formulas that I'm going to be presenting to you, there is going to be an S block formula. There is also going to be a P block formula. And then after that, there is going to be a D block formula. Don't worry about the F's. And looking at this shorthand electron configuration, we need to determine what is our period. The period is going to be the highest principal quantum number. So if we were to look at this element's shorthand configuration here, the period number is going to be 4 because it's greater than 3. That's easy. What block is it in? You have to look at the D. If the D is at the very, very end, or the S's or the P, doesn't matter, whatever it is at the very end, it is going to be the block. So ours is the D, so this would be the D block. It's that simple. However, it gets a little bit more complicated when we have to find the group number. The group number. How do we find that? There are formulas here. For the S block, it will just be NS. NS, the N here stands for the number of electrons in that particular block, that letter. So if it's NS, it means the number of electrons in that block, that S block in this case. Another formula that we need to use for the P block, again, all of these should be memorized. It's the NS plus the NP plus 10. The NS, number of electrons for the S block, NP, number of electrons for the P block, and then you just add 10. That'll always be constant. And then at the very end, another one where you have NS plus N minus 1 times D. This N here represents the NS. So NS, find that. Then you put it within the brackets here. Then make sure it's multiplied by whatever total number of electrons are in the D. The iron is actually AR. And it is 4s2, 3d6. All right, let's start this again. Imagine this here is iron. And iron, we need to look at the period number. The period number is going to be the number of electrons in that block. Our last letter at the very end of our shorthand configuration is going to be the D block, because it says D here. If it was P, then it would be the P block. How about the group number? In order to find the group number, you need to use one of these formulas here. And the formula we're going to be using is going to be the D block, because that is the block that it's associated in. So if this is our math, let's do our 2, because that is the number of electrons in the S block that we have listed over here. We're going to add that with N. Again, The n stands for the ns, so we can actually put an ns here if you want. 2 minus 1 multiplied by d. So 2 plus 2 minus 1 gives you 1. Multiply by d, that should give you 6. So 6 times 1, 6, plus 2 gives you 8. So what is our group number? Our group number is going to give you 8.